Okay, so once again, parametric curves. This is just to refresh your memory from last week. This is how we constructed a parametric curve here, based on the physics of the situation, with different forces pulling in different directions, and you end up with three variables. T time x and y are the spatial variables, and x depends on t. It is a function. Y depends on t is the function. Those are two graphs on the right. But then when you want a dependence of x and y, the actual trajectory through the sky, when you combine them together, the result is not necessarily the graph of a function. Okay, so those are called parametric curves. Any combinations of two functions. Remember, these two functions on the right, they produce that curve on the left. Okay, so those are the combination of two functions is in fact is what we call a parametric curve. Okay, so and then just to have an example of building something from scratch but without any physics, we'll look at the circle, which is simple enough and complex enough to illustrate the ideas. Okay, so if you wanna, the goal is to express represent the circle in a new way, not as an implicit equation that's over there in the middle. X squared plus y squared is equal to 4. Okay, so it's awkward. It is virtually impossible to plot. If you put it this way, x squared plus y squared is equal to 4, it is pretty much impossible to plot, because you do not express x in terms of y or y in terms of x. You have to go through every point on the plane and verify the condition. If it's satisfied, you plot it. If it is not satisfied, you don't plot it. So that makes your work respectively way higher. We saw an example of that sometime in the past. The way we have handled a circle up until now was by representing it as two equations. So by cutting. So you could cut a circle in two and have y equal 4 minus x squared and y equal negative 4 minus x squared. Okay, so that's a legitimate way to do it, but it is cutting, and long term that simply is not gonna do it for us. So you have one upper half, and you have the other one lower half. Okay, so long term the curves are so complex you cannot predict whether they have some kind of symmetry or any particular convenient way of cutting them into pieces. So you don't want to make the habit of this. So in other words, both of these methods, this one and that one, are bad for representing anything more complex than the graphs of functions. So even if we put aside anything kind of motion, which is very important topic if you think about motion through space, or it could be physical space, or it could be motion through any kind of man-made abstract space of whatever prices or behaviors or just data. Okay, so that would be dimension of the space will be way higher, but all the rules apply, and so we do not, once again, we don't want to deal with that. So the idea then is to eliminate from our equation, this one, eliminate, not eliminate, but rather come up with a way of representing the curve that we already know what it is as motion. And the answer is pretty much, if you just remember what the idea we actually we came up last time, is that the substitution, integration by substitution, which was also discovered, the idea of trigonometric substitution was discovered by looking at the denominator over there and realizing that it has something to do with a circle has something to do with the trigonometry, and that's why you come up with a trigonometric substitution, because that's where trigonometric functions come from. They're over there, the picture on the left. So usually you have a circle, and then you every point x, y produces the two x and y coordinates can be expressed in terms of the angle between the x-axis and the x-axis in the that radius from 0 to xy. Okay, so and then that's how, well, x is cosine of that angle and y is sine. Okay, so that is the idea, and the only, just in case, what we did here over here is that you can get back. So not only you recognize it as a circle, but you also can get back by just once again using trigonometry. And so this is the Pythagorean theorem: x squared, the sine cosine squared plus sine squared is equal to 1, and that gives us back our equation. So we'll see more examples of more just as interesting curves, or more interesting, more complex curves. At this point, we're just looking at the basics of this representation. Okay, so once again, the picture is on the left. The parameter, whether you think of it as time, when you have a rotation that is uniform in speed, okay, uniformly rotating, that is t over there, or you just think for every position of our radius, there will be a location on the curve, and there will be an angle. Okay, so either way, the representation is the top. X 2 cosine t, y is 2 sine t. So those once again two functions that have been promised, as you can see here, those two on the left. X depends on t, y depends on t. Whatever those functions are, absolutely no restriction on the choice of those functions. They will produce parametric curve. So this one, we just start with an example that seems to be important. Circle. A circle that is not the graph of a function, and at the same time is almost as simple as you can imagine. Okay, so so at this point, how do we can plot it by hand, or we can plot it with Excel, and so both of these will be happening. Let me start with. Computing trigonometric functions by hand may be not very interesting, so not a lot of fun. So I'll do it this time. I'll do it with Excel again. But the idea is, and then we'll do it, and then we'll do it, and then we'll do it with the other one. Okay, so I'm going to plot the circle based on our what we call parameterization. So our parameterization of the circle is right here at the top. We have two functions. We plot. What is it? We will have 3 columns for each of the variables. T will be independent variable, and we'll be entering values for x, and then for every value of t will be also y. Okay, so that row by row by row will have 3 numbers in each, and then we'll visualize it just the way we have. Okay, so all right, so we're going here, and so once again, I want to have a step increment of x equal to 0.1 that I like. I'll put t's here. X is here, y is there. Okay, so t is starting with 0, why not, even though it's pretty much arbitrary. So once again, this one is equal to the previous plus h, which is r3 or 3c1. Okay, so each time we'll add 0.1. Okay, so like this. Okay, now the Excel has all the trig functions, so it will be x will be cosine of what? Of this value of t. Okay, that's cosine of 0 is 1. Now y will be sine of the same value of this one. Okay, and it is 0. Okay, I could right away spread the formula down, and I have a bunch of values right away. Okay, let me fix this. Okay, so well, that's what is this? This is a parametric curve. Don't think of a parametric curve as an actual curve, because that is only just a visualization. Parametric curve is 2 functions, x of t, y of t, and if we sample them, which is what we did, you can visualize it. But otherwise, this is the whole curve. Okay, you can see how before you plot it, plotting is really revealing, but just looking at the numbers before you do that, it's also helpful. You can see how t increases incrementally at the same value, 0.1. Okay, now what's happening to y? It is decreasing slowly. well, actually it starts to decrease slowly, right, and then almost imperceptible, and then it decreases faster. Okay, and then if we look at y, it actually is increasing and but slowing down. Okay, so in other words, we can study these two functions separately and try to find out what's going on there. So let me do as I did last week. I will insert charts. For the first one. Okay, so this is the first one. X depends on t. Okay, X depends on t. So once again, you can highlight this and you can see the two columns that produce this graph. So X depends on t. There is no y involved. So this is the graph of cosine. This is a piece of the graph of cosine. It starts at 0. As you can see, it crosses 1 at 90 degrees horizontally, and then starts to decline faster and faster and faster. Okay, so that's what we know about cosine. Now I do the same with sine, not with sine, with y. Okay, so I highlight the two columns, one for independent, the other one for the dependent variable. Okay, so I go on and once again create a chart. So this one is this chart is for, there's no place for it. This chart is for it produces the graph of sine, right? So starts at 0. You can even see that it appears to be, look at the angle at the origin where the graph starts. It actually looks like it's 45 degrees, as we know what the slope is 1. That's what we know about sine. Remember one of those famous limits of about sine. It is 45 degrees 1, slope 1 for sine, and it is 0 for cosine. Okay, so and now finally, so this is once again, both functions are here with data. Both of the functions are visualized with separate graphs. So these are graphs of two functions. Now, however, the path, and that's a different word from, I'll be using it extensively, the path of the parametric curve, not the graph, not the graphs of the two component functions, but the path of the parametric curve is a combination of x and y with t thrown out. Okay, so I do the same. 3 variables can be combined pairwise 3 ways. I did 2, so now I do x and y. I highlight x and y. Okay, highlight x and y, and once again insert a chart, a scatter plot. Okay. Okay, so then what we're looking at right now is a piece of the circle. So those two graphs that were sine and cosine graphs going like this, I didn't continue on, but you can imagine that the first graph will continue as cosine up and down, the other one sine up and down. When we combine them together, we suddenly the result is entirely different. It is well, you can see that we're starting to form a circle. Okay, so the only drawback of the way Excel does it is that there is the directions missing. That is important thing for parametric curves, because it's not a big deal with graphs, because you know that the x-axis point, or the independent variable, pointing from left to right, so everything progresses from left to right. Here, however, you can certainly imagine when we have graphs, we have paths, we can go same path this way or that way. That doesn't matter. So here there is a way. Okay, fine. Let me. There is an alternative. Hold on a second. I think there is. Well, first of all, you can add data labels, which will be, that's exactly one of the best ways to ensure that what your visualization is to the point that you explain that indeed this is a parametric curve, not something else. So you add labels to all the points. Okay, so I don't think. Well, the labels are incorrect, unfortunately. The labels are, seems to be referring to, they're referring to, what are they referring to? either x or y. And what we want to actually refer to is what? Okay. T. So not x, not y, but t. That's actually you can do that because the data for this chart is only x and y, and t is thrown out, unfortunately. So Excel just doesn't understand that part. Okay, so but we'll see how we'll do it by hand eventually. Another way to progress here is to make sense of it. It's different. Everything is changing. I can find. So there is also an option of adding arrows, so that you know which way it goes. Okay, so we did it by hand. I could show you the full circle if you want to see more full circle rather than part of the circle. You just add more data. Well, almost like this. You add more data and more. There will be more points. Maybe it doesn't look like a circle, but if you keep doing it, it should look more and more like a circle. Okay, so here we go. It's more like a circle. If you can so it plots point by point. What Excel does, it points point by point. So each point on this graph is nothing but a pair of numbers x and y. They're plotted, and then Excel tries to figure out what that curve is, and it connects them by edges. Okay, so that's what's happening. Okay, so let's just copy this picture to back and try to illustrate what's going on. Okay, so a little bit smallish, but the point is here. So what we're talking about here is that this is x versus y. X versus y is what is being plotted, so there is no t. Now, what I try to, if I look at the back to my spreadsheet, I can see how t changes at 0.1 at a time. So if I want to put labels, this is how I put labels. I put t equal 0, t equal 0.1, t equal 0.2, t equal 0.3, and so on. Okay, so it's a trip. Imagine, well, that's what parametric curve is a road trip or hike, and you plan it ahead. So you have a map with two spatial variables. You're not just driving on a straight line as we did in Calculus 1, a straight line, one road. We are now in the field. We are going through the terrain. We ignore the elevation for the time being. You need the third dimension, but x and y are the two variables that we're dealing with, spatial variables. And then there is a time variable that we are planning ahead, or we do it after the fact, doesn't matter. Then this is how you do it. You put points on the map, right? You points on the map, close together or not, and then you put time when you plan to be at each location. So starting point here, then after 1 hour, after 2 hours, after 3 hours, after 4 hours. Okay, so that could be your trip, road trip or hike plan. Okay, and that's what it is. And then you certainly you feel free to connect these by arrows, and which even in reality will probably have some curves behind it. So you're moving along a curved path. Okay, so that's how you squeeze three variables into the two-dimensional space. So the plane is two-dimensional. You have only x and y; those are two variables, and there's only 2 degrees of freedom. So if you go on a trip, or you have a piece of paper, that map is two-dimensional. How do you deal with the third dimension? You label. Okay, so you label when. In addition to where, those dots are where, you put a label on it to say when, in addition. So that makes three variables. Okay, so that's the basic thing about trig, the circle. Okay, So, but just to get started on calculus of parametric curves is there are issues just as with graphs. We can speak of the same ideas as with graphs, and one is tangent lines. Tangent lines, so they will have tangent lines, and so every point has a line through it. At this point or any other point, there will be a tangent line. Okay? So where does it come from? It comes from the you don't want to go back and try to connect x and y. We know how to find tangent line when you have y is equal to f of x, which is fine, except we're not in that. We don't want to go back to calculus 1. Okay, so we want to deal with parametric curves as they are given to you as two functions. So you have to instead look at two functions. Once again, x is equal to x of t, y equal y of t. Two functions, and from this, somehow, these two functions, you have to figure out what the tangent line is. Okay, so so it is possible. It is certainly possible because, in fact, it goes back to Newton. You know, connecting tangent lines on one hand, and motion on the other hand. So that's how he, as I understand it, figure out what the meaning of tangents. Beyond just like circle, you know what the tangent to a circle is. It's what is a tangent to a circle? In fact, it's a perpendicular, a line perpendicular to the radius. So that had been known for a long time. The meaning of a tangent to a circle. The tangent to a parabola is more complicated, and on and on. It's complicated if you want to solve the problem in general. How do you do it? Well, Newton came up with the idea that thinking about moving along that curve, okay, by so physical interpretation of to solve a mathematical problem, okay, and then as I understand it, then once he developed calculus, he could go back to physics and then also all the physics problems that he can think of. Okay, so then one thing is, well, let's take a look at what we have. We have x equal cosine t, or the radius was 1, so fine, sine t. Okay, and then what we can find, we have two functions, we have two derivatives then. So x prime is equal to negative sine t. Y prime is equal to cosine t. Okay, so that's how the calculus of parametric curve starts, with the derivatives of just differentiating those two functions. It's the opposite of what we did with the physics and motion, those graphs that we did. We had the second derivative found, the first derivative found the original function, but you could start with your motion and then find your velocity. So that's what we're looking at. Is if you want to look at it from the point of view of motion, then you have location, x and y, as depends on time. This is time, still time, and this is velocity. Except this time it's not single number because the motion is two-dimensional, but two numbers, so it gives you how fast are you moving in the horizontal direction, how fast are you moving in the vertical direction. Well, both of them might be vertical, but if you have two axes, x and y, then you can measure your velocity in two different directions, and then these are the two functions that give you that. So it is you can actually look at what you have on the right and just match certain things, algebraic things, with the graph. For example, if we look at so starting with, say, t equal to 0, then x prime of 0 is 0. Y prime of 0 is 1. Okay? So if we look at this, can you see this on the graph? Well, here's the point. T equal to 0 is here. So this is t equal to 0. we look at the graph and then we ask ourselves, what is that algebra on the right? What does it tell us, or what is about it recognizable on the graph on the left? X prime is equal to 0, y prime is equal to 1. What does it tell you about the motion? Okay, what's the direction of the motion? X prime of 0 is equal to 0 means that your velocity relative to the x-axis is 0. So you either see it on the graph, look at it, the red dot followed by the blue dot, and there's virtually no change in the horizontal direction. Okay, so it is even better visible here on if we look at well, as you can see, this is x virtually hasn't changed. In 0.1 second, y has changed. Okay, we progressed up, and that is the derivative equal to 1, and this indicates the derivative equal to 0 pretty much, or close. And then that indicates the direction of our motion. It indicates, it tells us also what the tangent line is. What's the tangent line? What is the tangent line through that red dot over there? Well, I mean, if you know what the tangent line is, you know how to plot a tangent line. Well, just try to forget the fact that this is not the graph and just try to plot a tangent line. How do you plot a tangent line? What does a tangent stand for? Greek or Latin for what? Touch. So the tangent line is supposed to touch the graph at that point, so what is it? Well, I mean, this is the end point. Let me maybe push it back. Okay, so I pushed it a little bit back beyond 0. So look at what does this look like? This is almost the tangent line. So what is it? Look at these numbers, these points, 3 consecutive points.
There's more points on the right side of the circle than there are on the left side.
Well, I just didn't plot the whole thing. We are looking at, in fact, what we are doing right now, we are trying to zoom in on one point. So we don't really care what's happening elsewhere, but rather, well, let me...
I was talking about like the distances, points of t.
How about this? So I'm going to zoom in. How about I zoom in? How I will make the interval of t smaller. Than 0.1, let's make it 0.01. And here, say, well, unfortunately, Excel keeps rescaling it, and as you can see, the point that I'm trying to make is kind of disappearing more and more. So no ideas of what the tangent line is? This right here, what's the tangent line right here?
Is it 1?
Well, 1 what? What's the line? How do I plot the line? What does it look like? It will be a vertical line, right? It will be simply a vertical line, and As you can see, if you look at the, it is almost a vertical line. If you look at the scale, look at how small numbers here, how little the numbers change here, and vertically they change quite significantly. So this is in fact was already almost entirely a vertical line. Okay, so once again, look at it. 0.1 versus 0.1. So this is more or less proportionally. This is more or less proportionally. Is it? Yeah, it's roughly proportional, but really you can zoom in more and more, and then you will end up with nothing but a straight line. So so literally this is the tangent line. Well, so why is it vertical? Because x prime of 0 is 0. So there is no at that moment of time there is no progress to the left or to the right. If you speak of instantaneous velocity. If you think of motion, you remember what the meaning of the tangent line, if, well, we just came up last time, or last week, is what happens if you were, well, the example was what happens when the gravity disappears. You go off on tangent, remember that one? Similarly, you are rotating an object, or whatever it's called, on above your head, and then what? So the object going circular along the circle, and then you the rope breaks. What happens? It will go along the tangent line. Okay, so this way, not only we know that it's going to go tangent line, but also we know which way it's going to go. So as you can see, if our parametric curve is oriented appropriately, we know which way we're going. Then we also know that it's not going to be just a tangent line, it's going to be a tangent vector, in the sense that we know that we are going in that direction, not this direction. Okay, so it is an important concept of tangent line as well as tangent vector to a parametric curve, because that's where things are going. That's where the object will go if whatever the force that was holding it and moving it disappears. It is also the direction of, say, headlights of your car. So if you're driving along that road over there, the blue road, at every point where your headlights point, they point along the tangent line forward. Okay, so that's why the direction matters. So these are your headlights, and these are your headlights, and these are your headlights. They will be pointing off the road in the direction opposite of the turn. Okay, so but this one is certainly already gives us the idea of what parametric curves give us in addition to what we had in Calculus 1, and that is we have a vertical tangent line, which was not allowed in Calculus 1, because that would indicate that your function is not differentiable. Example is this. You might see a function like this. This is a totally fine function. What is a cubic root of x? A cubic root of x, and what it has a tangent line that happens to be vertical. So even though it is totally, there are no breaks, there are no cusps on the graph of the function, they might have, however, a derivative that is vertical, and then we discard this function. We call this function, as I said, this is not differentiable. So not differentiable at 0. Cubic root of x, there is really nothing wrong with that function. However, it is based on judging by Calculus 1, there is something. Why? Because the tangent line happens to be vertical. So vertical means that the derivative is infinite. Okay, so it's not differentiable. So we discard it as certain things cannot be done then when you face something like that, including the fundamental theorem of calculus. But now we are beyond that. There is nothing wrong this time with this curve. This function will be totally differentiable, and but what does it mean for a parametric curve to be differentiable? It's simply that both of the functions are differentiable. So it doesn't matter what it's going to look like. It might look very weird. We are allowed to do any kind of model any kind of behavior with the parametric curves, any kind of motion, including like this. There's nothing really weird about it, but we could model things like this, for example, like going up and down like this. There is nothing wrong with that. We can have spirals. We can have just convergence to a point, either over infinite period of interval of time or not. So all of that will be covered by parametric curves. And there, once again, it doesn't matter what the path looks like. So these are paths. Okay, so they might look weird, but the graphs behind them might be very, very well behaved. So it just happens that the examples that we have considered that produce the curves that are nicely behaved, because that's what we want. We wanted a circle, and now we have a circle. But generally, you can think of very nice nasty functions produces nice curves, and nice functions producing nasty curves. So everything is possible because every motion is possible if you think about it. Okay, so that is one example. Now I want to do a very simple example and do something by hand. Because just like in Calculus 1, if you're plotting graphs, you got at least few times plot graphs by hand before you do them with a calculator or even Excel. The advantage of Excel, at least it shows you the data. So this is the data, it's all here, and you're plotting it, you know that it's plotted point by point. And you do it because for a single reason that you don't want to do so much work by hand. But you should be able to at least do a few. So, so the idea is, well, let me refresh your memory about plotting graphs or plotting curves. So in Calculus 1, you have y equal f of x. What the graph is not important. All you get is the data. So say x and y, and you have, say, 0, 1, 2, 3, 4. And then you have outputs y's, maybe 1, 2, 2, 3, 5, 4. Okay, so that might be your data. So it's just a function represented by a table and nothing else. Okay, so this is Calculus 1. And then you're supposed to be able to plot it. How? One by one point at a time. Okay, so I take this point, 0, 1. It's here. Okay, then I take the next one, 1, 2, over here. And then the next one, 2, 2, here. Then 3, 3, and 4, 4. Okay? So that's how we do it. Just to refresh your memory. Okay, so once again, by hand, all you need is a lined paper. You draw axes. You have your numbers. So for x and y, you put the scales where they belong, and then every pair of numbers, input output, is a point. You put it on the xy plane, and that's your graph. You connect it by a curve if you can think of a reasonable one. Okay. Okay, so that's Calculus 1. Now Calculus 2 is more complex when we're talking about parametric curves now. So that we'll still have a table, and we already saw that we're going to have 3 columns, t, x, y. So not to be confused, once again, this is input, output. Now, the way we have renamed things, we have t, x, and y, and I put a thick line here to separate input from output. So the input, as you can see, is pretty much the same, just a bunch of numbers. And then the outputs are pairs of numbers this time. So like I said, it's 2 functions. It's 2 functions, just they kind of merge together because they share the input variable. You then merge them together to create, rather than having two tables with two columns, you make them together and have one table with three columns. So say, let me put the same numbers here, 2, 3, and 4, okay, and I don't know, 0, 0. Okay, so it doesn't matter what those numbers are. So once again, x of t, y of t, input, output. And at this point, what do we plot? I still have two functions. So I want to make that clear. Those two functions, they don't go away. I could have those tables. I could plot them just the way we did it over here. We have x and y of t plotted separately. But that's not really what we care about. Let's assume that we already know how to plot single function at a time. So plot both as before. As before meaning calculus 1. Okay, so that's the statement is there. So that's what we did, especially with Excel. It is quick. So those two graphs of x and y, you can still see the one and the other. This one, this is x on t. This one is y on t. This one, y on t. And then, but our real interest is that. So if you are studying motion, you want to see what the motion is, what trace is left by the object. So we're plotting x, y. So what do we plot? I want to plot the path. What do I plot? This is the data. What do I plot? Well, first of all, where is my path located? Well, this is the one I'm talking about. What is the plane that we're talking about? So there are three variables, t, x, and y, and the way you can see it is what the two variables are highlighted on the left are x and y. So the whole thing is happening in the xy plane. So we have three pairs of variables, tx. Where do we plot it? This one. Where do we plot this one? It is tx plane. Okay. Where do we plot this one? This one. Go away. Where do we plot this one? ty plane. Where do we plot the last one? xy plane. See how the variables are highlighted. So the answer is, whenever we're interested in the path, x and y combined, the answer is the xy plane. So pretty much the same answer, but the meaning is quite a bit different. So t is gone, and both of x and y are the two dependent variables. And so that's what I do. I take then I plot these. Okay, so once again, I do have to ignore t because I do not have the ability to plot in 3 dimensions, or at least for the time being in the current state of technology. I cannot do, I wish I could, 3-dimensional, like some kind of hologram, and I put dots in space and drawing 3-dimensional things. So far we have to stick with the 2-dimensional plane. Okay, so then I'm plotting 1, 0. Okay, 1, 0. 1, 0, that's my first point. 1, 0. The second one is 2, 0 here, the second point. The third point is 2, negative 1. So 2, negative 1 here, the third point. The fourth point is 3, negative 1. 3, negative 1 here. And finally 4, 0 is here. Okay, so this data is plotted here. Once again, you might try to imagine what the graph might look like. Might look like maybe there's some path somehow. You can imagine this is some kind of function sampled, some parametric curve, two functions sampled, and you produce this rough outline, rough curve. This is incomplete. In what sense? I still certainly I want to indicate the numbers here, 3 or 4, but that's not really the interesting part. The important part is to label the points. So this one is t is equal to 0. The green one is t is equal to 1 over here. So my curve is labeled with values of t so that we do not entirely abandon it. So this is t is equal to 2. The purple one is t is equal to 3. And the black one is t is equal to 4. Okay, so we have labeled them, and if anything you want to add to here is indicate the order, even though labels certainly tell you the direction of motion. But still, just to make the picture better, this might how you might want to plot it. Okay, so that's how we're gonna continue on. Okay, see you next week.